right. Hi, everyone. Thanks for coming to today's colloquium presented by Ridhi. We're talking about cilia synchronization and how we can model them using hydrodynamics. So take it away.
you. Um, yeah, so I'll be going over a little bit about what Cilia synchronization is. I was working in this lab over the summer where this is my project. I don't know how useful it was at the end of the day. We haven't found out yet, but this is kind of what I did, and I think if nothing else, it's as undergraduate students, it's nice to like look at how like you kind of develop a model just in general. So we'll be talking about the experiment we did, the initial data analysis that I did, kind of the foundations of Cilia synchronization, which is kind of key to the model I made to explain that. Um, yeah, so what is cilia synchronization? Cilia are these hair-like organisms that are found in a lot of different surfaces in the body. So your lungs, your pancreas, and the lab that I was in really like the PI is kind of at the top of the piece of cilia synchronization in various different things. So there's like motile cilia and non-motile cilia. Non-motile cilia don't move, so this can be something like in the pancreas, which are for signal detection and stuff like that. I was more interested in motile cilia, which are able to move and they kind of like oscillate back and forth and in a circle. Um, and yeah, they're really key because they kind of are responsible for moving things. So if you think about your lungs and like you cough up mucus if you're very sick, which is what I've been thinking of because I've been sick. Yeah, that mucus is moved by cilia, kind of like moving it on top of them, kind of like a football stadium wave, which is interesting. Which and study that. Yeah, so this is maybe like a bed of cilia. I think on the right is motile cilia, on the left is non-motile cilia. Um, and metachronal waves they kind of make look like that, where you can see that each like it's local interactions, which is interesting, right? But like the overall effect is big, kind of like neurons, right? Like there's a lot of neuron like interactions are all local, but the actual effect they have only kind of shows up when it's a lot of them. Yeah, it kind of also makes cilia difficult to study since the interaction we want to study is local, but all we can really look at is the big effects that are happening, the big waves. And so this experiment was interesting because it kind of like was able to isolate one cilia. These beautiful drawings are my um, they kind of refer to what the section will talk about. So call me an artist, I guess. But yeah, don't judge me too harshly. I wanted to be artistic back in the day. So some of the things that we're kind of talking about when we look at cilia is can, or I guess what this experiment specifically talks about is do cilia synchronize, which is an artificial source of oscillations? Like, are they synchronizing because there's different cilia around? Like, what is the base of synchronization? Is it like structural? Is there some sort of signaling happening? We think it's mainly hydrodynamics based. Of course, there's a structural component and like signaling and whatnot, but it the easiest way, and I think biology usually tries to the easiest way. Don't quote me on that precisely, but is just to like go with whatever the simplest way of synchronization is, which is hydrodynamics, right? They're all in this fluid. So if something's moving in the fluid, it's making these waves and it affects the things around them. So that's this experiment's focus. And then, of course, if we're talking about hydrodynamical interactions, we want to know what frequency does something need to be oscillating at to be important or like detectable by nearby cilia? How far can that synchronization like really be? Um, yeah, so this is a video of so this is a video of the experiment. This is a cilia. It's so bad, but this is like a cilia. If you can see the little, yeah, the little worm is an actual cilia. And then the one of the postdocs there kind of made this thing, which is an artificial actuator. So we kind of record the cilia. We're like, how fast is this moving? Blah 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 blah. And then this actuator starts moving at some point. Yeah. Um, and this is the actuator is of course moving at a fixed frequency, and so we kind of see if there's a change in the frequency of the cilia, and how it responds to different frequencies, different distances. Well, actually, I don't know if they did different distances in this, but we modeled different distances, and I think those are maybe the next steps of the experiment. But definitely different frequencies. Um, yeah, and of course, it's at the 12 uh, micrometer. I think it's. I usually just see the muse on like micrometer scale. Yeah, what it looks like. If you can see, the initial thing was very artistic, right? Okay, this is another artistic clue of the next section, but yeah. So I did a lot of like the visual analysis, right? Like, as you can see, our data collection is a very sketchy video. And we're trying to get some actual quantitative information out of it. So the first step was obviously like, how can we extract information from this? And so of course I showed up at the lab, and my my supervisor just gave me a bunch of pictures that look like this and was like, this is how we recorded the data. So we need you to extract something, which was fun. So what we're looking at here is a chronograph. On the y-axis, going up to down, is time. Well, time needs to be like multiplied by some constant to be the actual time in seconds. So that's like a time axis. And then the rest of the x is just pixel space. Like there's no, um, like it's just showing movements. These like streaks are just the movement of the actuator in these. Yeah. So it's just pixels compared to time as it goes down. So as you can see on the, if you're looking at it, then on the left is the cilia, the biological cilia, and that's moving at some speed. Like there's, the streaks kind of represent its like oscillations. And then on the right, the actuators is off, 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 and then it starts moving. And so we want to see kind of like how the cilia behaves initially and how it behaves afterwards. And so like a lot of the images I got would just simply kind of look like this, and there are different frequencies. This one was around 15 hertz. This I think had the closest synchronization to what I saw. Um, yeah, and then I think the cilia itself, of course, like the cilia doesn't move at a specific frequency; it kind of does whatever. So I think, but it moved around 15 to 20 depending. Yeah, and so this was kind of the model, the code I wrote to detect the movement changes. Yeah, so on the y-axis is the activity, so I guess the amplitude changes, and then the time axis, um, and so it's not moving, and then like I don't know, it detects it, and it just you know this is a detection. So it looks very simple, but guys, I went insane over this assignment. But looking back, I was like, simple enough, but um, yeah, a lot of breakdowns over this. That's good. Um, yeah, so this is kind of an example of one of the data sets we got. So this was the 15 where we had like the most synchronization. So the orange oscillations is the beam, or like the actuator, and then the purple is the cilia. And you can see they kind of like their phases align. And of course, we're looking at, I don't know if I made it clear, but yeah, we were only looking at phases. Just because it's maybe the best way to tell if something's synchronizing or not. But you can see kind of like we don't know if it really aligns, right? Like if we don't know if this alignment, like it kind of goes in and out, but it's very like on the same line. So we don't know if this is like true, hmm, what is it? Synchronization. We don't know how much of it is by noise, how much of it is actual. So we need to also have a model and like some sort of expectation of what to look for, right? To figure out our error. But yeah, so we had synchronization. We had different frequencies that were not synchronized. So in different frequencies, the slopes of the lines would be different. So these were clearly synchronized. But I guess the next phase was we need to create a model so we can figure out what we're actually expecting to see if we're actually seeing synchronization or not. Find something like that. Yeah. Uh, so this was another way to kind of see if it was synchronizing or not. Just like a lot of it was really an issue of like what are we looking at because the data is so noisy. You saw the video, like that's the data, right? So it's very very noisy. So I tried a few different like techniques to kind of like visualize it. So this was another one. This is the power spectral density. So it's just um I don't know like how much synchronization is like what the frequencies this density distribution is. So as you can see here, the blue line is the cilia before the actuator turns on, the orange is after, and then the green is the beam frequency. And as you can see, there's a shift towards it. Like the blue after goes to like where kind of the beam is. And this is Hilbert transform, so it's just kind of it just like turns it into like waves like sine data. Um, yeah, and then this is an example of a not locked system. This was on 20 hertz, so it was I think too fast to lock in with the cilia. So there obviously there's like a range where it locks. And as you can see, the slopes are different. Yeah, I mean, yeah, and then the phase difference I also have in both like graphs. I think back here as well. But it's so noisy that it's almost not. The difference is almost more useful. And then this was what it kind of looked like for this. But the interesting part here was it looks like the cilia shifts still, even though the frequencies are not very close together. Like the cilia, there's a little bit of a shift. So now we want to know is maybe it's not so much like binary, it's like if it locks or not, but there's like a range of frequencies where it locks, and how like we just need a model is the next step. So that is what I worked on. Um, yeah, I'll just say noisy systems also. Like this is maybe also something kind of having phase locked on, though they kind of go out of phase, and it's very, very noisy, as you can see. So yeah, the next step model. So we have to figure out what the physical mechanism of synchronization is. And like my lab, we focused on hydrodynamics. I will drink a sip of water. And again, the picture is a clue. Not very well drawn clue. It is a clue. Okay. So this is the model I used. I got very lucky as I was looking at all the books in the lab, and I came across this one that solves half my problems. And so this is the fluid dynamics of some motility by Loga. And they had this model, which is interesting, where they're also modeling cilia synchronization just purely through phase dynamics. And there's been experiments earlier to like show that you can have synchronization purely based on hydrodynamics and and so in this situation, I guess I can kind of walk through what is happening here because I was very confused the first time I saw this. We are modeling cilia as these like circles, like the black circle and the white circle, and they have like some radius of a, and they are moving in a circular path. So you can kind of think of it as like this like L boundary is where the cilia is locked, and then it's kind of like going like this. Um, and yeah, this is a no slip boundary, which basically means there's no movement on that boundary, which makes sense because we want the cilia to be attached, like the base thing. Um, yeah, of course, in our situation, like it's a 12 micrometer, you know, it's very small. So the distance between the two cilia is much smaller than the distance to the boundary itself. So we can just leave out the boundary, kind of like if you're kind of trying to figure out how something is moving in the ocean, for example. And if it's moving in the surface, on the surface, you need to kind of like take into account the surface. But if it's in the middle of the ocean, you know, the surface is too far for it to make a difference. So because it's too small, we are just gonna leave out that boundary in our calculations. But this is what the book used. And yeah, they're both moving in some radius, one or two, and they are have like some phase um, Greek letter one or two theta, not theta. That's phi. Yeah. Um, and of course, there's this other mechanism where it's like some sort of push pull reaction of the radius itself, but we are going to skip this and just do phase. And it was theoretically shown in this by Uchida and I'm not saying the names right probably, but they showed phase dependent things can happen experimentally later, and these are the equations for it. Um, yeah, I don't know how much to go over the math of it, but essentially, if you just kind of look at it, you know that. Um, so if you're just looking at it, right, um, phase differences is dependent on the force that the cilia is experiencing. So, um, yeah, like so I just kind of looked at each cilia and I was like, what is it experiencing? So of course it has its own internal forces, right? Which kind of makes it like internally move at whatever frequency it wants. And then it's affected by the velocity of the water here, the changes caused by the other cilia. And so those were the two components that I was looking at when trying to figure out what an equation should be, because my supervisor were just like, yes, you should just figure out the math behind it. And I was like, of course I'll do that. And so the first step, of course, he was like talking through like what things to consider when trying to like make the equation, and then the book itself also I got very lucky had kind of its own mechanism. But yeah, those are like the two things you're considering: internal, external forces. I think that's the case with like all of physics, right? Um, so these equations here, as you can see, the first is they're identical if you have like two cilia, but of course this like simplifies a little later because we have an actuator. But this one you can see is the this thing. I forget the Greek actual Greek name for it. This is your viscosity change. It's Stokes drag. Um, I yeah, like we just drag essentially. As you know, I'm sitting, but yeah, that's just drag. I think R naught was radius, the radius of the circles, I believe. Um, Again, this is a while ago. I should have reviewed this, but it is, I believe, the radius because we're keeping the same radius for both Cilia and actuator. Force theta or phi one is the internal force, and then this entire term is the external force. I the derivation for that term is a little long, so if anyone's interested, I would recommend looking at the book, which is mainly where I got it from, and then I modified a little bit. But yeah, it's essentially just how the force of the other cilia is affecting the area around. So yeah, and that's identical for the other. And then beta is like a strength term essentially, and then we can more simplify it for the actuator, which we'll call two in this case, phi dot phi two, because we control the frequency of that, and this is essentially a frequency, right? Like changes in phase. So that's just some frequency that we choose, maybe. And then the force term also simplifies because of that. Did I go over force? Okay. But yeah, and then we get this force term, and then this. Again, this is kind of a long derivation. I guess trust. But I can also, I don't know if anyone's interested, I can send math and also I would check out the book. You can derive the terms I got fairly easily if you same simplifications I did. But yeah, it's kind of what we're going off of. Oh, and this L is the distance between the cilia and actuator. Hopefully that makes sense. Like I know I just like brushed through a lot of math, but yeah. So using this, I oh well, look at what this gives us, right? This gives us the phases that we'd expect for the two, the cilia and the actuator. It gives us the force, and so if we can use like um we can use this information to figure out what the next step should be. So you can do like what is it called? What is it? The Euler's method stuff. Um, Euler's method. You can like derive what the next step should be. As you can see, my math names are very good. But essentially, what I got was this model. I should have used different colors. I was going to change it before this presentation, but I did not. So we're back here again. But this is just showing like on the x-axis, you have actuator frequency. On the y-axis, you have distance between actuator and cilia. And you have this like color coded graph of what the phase locking strength should be. So there's a middle portion, of course, where actuator frequency is perfect. If they have the same frequencies, of course, they're phase locked. And then there's like this like section here in the bottom where it's like the black like areas are where there's not phase locking, and you can see those sections if they're very close by, they'll phase lock. And then there's also apparently like layers of phase locking for like levels of phase locking that we kind of thought of. Um, and interestingly, there seems to be some sort of like asymmetry when you use the equations. As you can see, like it's kind of like on the other side, on the left side. Um, it seems to like have some sort of preference for the right. Um, yeah, those are some things to kind of look for in the future. But I mean, don't quote me, but it might maybe also makes sense since if you're thinking of like biologically, the cilia are moving in a wave, there might be some sort of like direction they want to go at, and not so much like go everywhere. But yeah, this was the model. I don't know. I think they're using it still and like trying to kind of add more stuff to it. What I got. Yeah, that's essentially it. Next steps, of course, is to confirm if the model actually works and actually compare to experimental data. I ran out of time for that, but I think they will be doing that. Farzan is the person who made the actuator, so yeah, that's essentially it. I know I brushed through a lot of like the more technical details, um, but yeah. Any questions, complaints, or concerns? Um, well, I mean, on the the distance is on the y-axis, right? And then the actuator frequency is on the x-axis. So yes, I think actuator frequency is a big thing. But again, like if even if an actuator is moving, if it's too far away for the actuator, yeah. So like of course distance matters. That's kind of what we're speaking. Like our experiment really didn't vary the distance enough. So I think that's a next step because it's such an important part. But um yeah, like I think distance is kind of key. It is in the equations and it does show up and stay there. So mathematically, it's definitely there. And I mean, even if you think about it logically, it should be there. But it does look like actuator frequency. Yeah, not experimentally. I think that would be the next step if I ran out of time. But I think we definitely should because yeah, we didn't. This was just mathematically based. This is just a mathematical model. This is not based on experimental results, which is why the next steps are experimental. So this is based on uh like these like terms where you're like if you know because you have like how the frequency is supposed to turn or like change. So we can like add in distance terms and the beta term is just the distance from the distance between the actuator and frequency. You can add if you know the phases. We have like the phases here, right? And we have the derivate like the derivation derivative terms. First derivative. I swear, guys, before the we have a first derivative, so we can like model what the next step should be, right? But yeah, this is purely it's just mathematical. Um, yeah, I brushed through it a little bit because it took so long to do, so it might be a little bit too much math for what the colloquium really is. But yeah, I would recommend like checking out the book, or if anyone's really that interested in the math, I can definitely provide it as well. But yeah, this is modeling. Yes. Yeah, yeah, yeah. Yes, actually, that was what my next step. I just ran out of time. So yeah, that's kind of what I wanted to add. Like I had a almost like a white noise model because like that's like you can search it up and there's already code existing for like how to account for white noise, and I'm like might be a good start. So I think yes, definitely this model is very preliminary. You definitely need to add noise to it just because as you said, very very noisy data. Yeah. It's one cilia and an actuator. Yes, essentially. Although the other cilia, of course, like if it's two cilia, their equations are slightly different. Like it's this, like without the simplification. Um, we kind of, I mean, of course, like cilia research has been done for so long, and it's we really like what the focus of the experiment was to like isolate it to one cilia, and it's really difficult to do. Like this actuator is not. I don't think people have done it with an actuator before. Like I don't think it's been done before. Well, last time I did my literature review, I don't know if it's changed yet, but yeah. So it was unique in the sense where we're like isolating a single cilia. because we purely just wanted the model of how, like, the least, like, like, we only want to isolate for how frequency and hydrodynamic changes affect a cilia. So yeah, this is just studying that, and that's the way to isolate it. Any other? I hope that was okay. I don't know if I went too much over. Yeah.